Welcome to January 9th LeetCode Challenge. Leaf similar trees. Consider all the leaves of a binary tree from left to right order. The value of those leaves form a leaf value sequence. So we're given a binary tree here. For example, given above, the leaf value sequence is 6, 7, 4, 9, 8, given as such here. Two binary trees considered leaf similar if their leaf sequence is the same. So return true if and only if two given trees head node root 1 and root 2 are leaf similar. So at the end of the day, it doesn't really matter what the binary tree is as long as their leaf nodes are in the same sequence. Example 1, we have the leaf node being 6, 7, 4, 9, 8, which is equivalent to 6, 7, 4, 9, 8 of the second binary tree here. However, if the order is reversed, for instance, this is leaf 2, 3, while this is 3, 2, the result is false because they are not leaf similar, because the order matters. Constraints: the number of nodes in each tree range between 1 to 200. Both trees are given values between range 0 and 200. Alright, how do we go about solving this? So intuitively, let's find a leaf node sequence given both trees. Afterwards, we can compare them to see if they're equal or not. So ideally, identify the leaf nodes of the tree, and then of one tree, and do it for the other. So to find the leaf value sequence of a tree, we should use an option to be a depth first search. Our depth first search function will write a node of a leaf's value and recursively explores each child. This guarantees to visit each leaf in left to right order, as the left children are explored before the right children. So let's write our depth first search algorithm first. So DFS would be public. Alternatively, you can also do public void depth first search, and we're going to be taking the tree node, and we're going to take the list of integers called leaf nodes, or leaf values, I should say. Alright, should do some cleaning here. So our depth first search function will work as such. We would do standard depth first search, node equal null, then continue if node dot left equals null and node dot right equals null. Then we have to add our leaf value, values dot add, and we're going to add the node value, and then we would exit this loop, and we would do it recursively for depth first search. So we depth first search of node dot left would pass the leaf value list of integers. We do the same thing for node dot right, and we pass the leaf value list of integers. So this is our depth first search function, and we want to be able to call our function right here. Just gonna edit this, remove this, do this. So we define two lists of integer, and this is going to be leaves 1 for the root 1 tree, and we're going to call it new array list. Define another list for integer leaves 2 for the root 2 tree. Next thing we want to do is call depth first search on the first root 1 with the leaves, passing it recursively. Define the leaves, and then do the same thing for depth first search of root 2, passing the leaf list of root 2, and then we want to return the boolean if the leaves 1 is equal of the leaves of the root 2 tree. Alright, let's run this. Submit. So we can see that time complexity wise is big O of the length of root 1 and the length of root 2. So if we call, so big O of the length of root 1 plus the length of root 2 of the given trees. Space complexity is also the size of the array of the leaves. So because we store each tree, we store each value of the leaves using a list. So we have 2 lists. So space complexity would be big O of the length of the trees as well. And that's it. Using depth first search to solve leaf similar trees. Have a good day.